a good question.
We are very happy to have Zach Bogorad from Stanford University. He will tell us about astrophysical constraints on long-range interactions of dark matter. Okay.
All right. Yeah, so hello, everyone. Thanks for the invitation. Yeah, so I'll be talking about long-range constraints, constraints on long-range interactions of dark matter. I think if you saw the abstract I sent out, it probably, from what I remember, it focused on interactions of dark matter with the Standard Model. For various practical reasons, mostly that one paper's out and one's not. I'm actually going to focus probably on dark matter interactions with itself, but I will get to dark matter interactions with the Standard Model too, so if that's what you're interested in, I promise I'll get there. We will talk about both. But yeah, this is some work with Peter Graham and Hari Ramani, who are both at Stanford. And yeah, so we recently put out one of these papers, and the other one should be out soon, if you want to keep an eye out for that. Okay, so what am I going to talk about? I'll start, as I said, with dark matter self-interactions. And I'll begin by talking about constraints at short ranges and at long ranges, in particular at essentially infinite ranges, which are the regimes that people have thought about a lot in the past. Right? And so there's a variety of constraints people have set in these limits. The focus of this talk, though, is going to be the sort of intermediate regime. It's going to be a regime where the range of the force matters. You can't treat it as being infinite ranged anymore, but it's still a lot larger than the interparticle spacing in some system that you're looking at, and so you shouldn't think about this as some short-range hard scattering thing. Near the end of the talk, I'll switch to talking about interactions with the Standard Model. And here, most of the existing constraints, in fact all of the strongest ones, come just from combining constraints on dark matter-only forces and Standard Model-only forces, and I'll explain how that works. But then I'll present one new set of constraints that we've worked out that looks at ultrafaint dwarf galaxies and dynamical friction. Okay, so let's go ahead and start with the self-interactions case. So why is this a thing you might think about? Right, there's a lot of reasons people talk about self-interactions of dark matter. The sort of classic answer here is that when we simulate the formation of galaxies and then we compare what we get with what we've actually observed, these things don't quite match up. So you've probably heard, for example, of the core cusp problem, right? This question of how peaked dark matter distributions are in the centers of galaxies. But there's various related examples. There's the missing satellites problem, referring to the lack of satellites around the Milky Way, or void emptiness, where we see overly large voids with no halos in them. But these days it's also become common to talk about something known as the diversity problem, which is shown off to the right. And so this refers to the variety of slopes of rotation curves that are seen in the centers of, here it's ultrafaint dwarfs, but we see this in other galaxies too. It's not actually clear how real these problems are. This is sort of a recent thing. I don't want to get into it too much. I'm not an expert. What I'm told, though, is that more recent simulations have sort of increased our simulation uncertainty on a lot of these. And so it's no longer really clear that simulations don't actually match what we observe. Yeah, go ahead.
Can you explain a little bit what the bar data and the black line means on the plot? Is it prediction?
Oh, good. Yeah, I think the black bar here is basically a prediction. I mean, really, the black bar is an NFW profile, which is not quite what we get in simulations, but it's close enough. The blue data has nothing to do with what I'm presenting here. The red is just, measurements of rotation curves.
And NFW is lambda CDM?
Well, again, so simulations of lambda CDM don't give quite NFW, but they give something close enough for these purposes. The real point in the diversity problem, right, again, as opposed to something like core cusp, the real point is just that simulations show relatively consistent slopes. So if you just look at the slope of these red points near the center, they give much more consistent slopes than what we actually see in practice.
Okay.
Yeah, so we don't understand why there's such a variety of central rotation curves in galaxies that are otherwise pretty similar. Good, but again, I don't want to make strong claims, right? Recent simulations have increased uncertainties on this. It's not clear that simulations strictly don't match what we really observe. On the other hand, while it seems like you can maybe fit away these problems individually, it's not clear that you can fix all of them at once. It's an open question. So, historically, and I think to a certain extent this still holds up now, one reason to think about self-interacting dark matter is that it can help alleviate some of these tensions, right? You can change structure formation in a way that gives you, at least in simulation, galaxies that look more like what we observe. That's not the only reason. Oh, go ahead.
I just wanted to make a comment. So this is all assuming CDM simulations, Burrow, Frank, White, etc., assume a steady state. And if there's anything we know recently, and that is galaxies are the product of dynamic interactions, which are ongoing.
Yeah.
Even our galaxy is about to collide with something else, and on a time scale short compared to these simulations. So it could be a mix.
No, right, absolutely. Again, I don't want to make strong claims that like we can't explain the observation of current galaxies. There are some tensions. It's unclear to what extent they can be resolved with just very much standard model process, or I shouldn't call them standard model processes when there's dark matter involved, but without introducing additional interactions of dark matter. Yeah. But there's other reasons you might think about these kinds of forces, right? One is just, look, we can write them down, right? We don't know very much about dark matter. There's no particular reason it shouldn't interact with itself, and there are lots of interactions we can write down for it. Some models of quintessence also specifically introduce new long-range forces between dark matter particles. So, okay, this is a thing you can think about. It might be out there. You can debate exactly how likely it is, but it's a thing we should check for, right? And turns out we can set constraints on it. So what kind of forces are we talking about? Mostly in this talk, I'll use, to some extent for sake of example, a Yukawa-like force, but this is a sort of pretty generic thing that you get. So this is a potential between dark matter particles, right? So potential V, that looks like some strength relative to gravity. So alpha, and I'm writing alpha dd here to emphasize that this is a dark matter force, because later on we'll talk about other forces. So dark matter force with some strength alpha times gravity, right? This is just Newton's constant. And then, all right, it's proportional to mass squared, because again, we're doing forces, we're doing strengths relative to gravity, over r, just like gravity, but now with an exponential decay, right? There's some range lambda, likely corresponding to an inverse mediator mass, right? So lambda is just 1 over that mass. And beyond that force, beyond that range, you start to fall off exponentially. I'm, being a little loose here, right? For starters, I'm pretending that every dark matter particle is the same. They all interact the same way. Maybe that's not exactly right. Maybe you have a few species. Maybe they have slightly different charges. This is just meant to be sort of schematically illustrative. The one thing I do want to emphasize, though, about these situations is that while a force like this can generically be attractive, it can be repulsive, it can also be like electromagnetism in the sense of sometimes being attractive and sometimes repulsive. For the first half of this talk, I'm not going to consider cases in which your dark matter is net neutral. So this is not applicable to something like millicharged dark matter where you have equal amounts of positive and negative charge. Right? We're going to be looking at coherent effects from forces from large collections of dark matter particles, and if those dark matter particles are net neutral on these kinds of scales, you just aren't going to get any of these effects. So this isn't going to apply. But it will apply to both attractive and repulsive forces, although we'll talk about slightly different constraints in the two cases. Yeah?
Why do you assume that the dark matter interactions are proportional to the dark matter mass?
Good. So this is mostly just a convenient parameterization that's become conventional, in part because sometimes these things are phrased as violations of the equivalence principle, right? If you have a single dark matter particle, you can just always write things down this way. If you have a mix of species, well, this won't necessarily be true for every pair of particle,
right.
But also I'm looking at large scales, it's a mixture of dark matter particles, unless you somehow have a crazy system in which you have drastically different dark matter species populations in the two different ones, it's just not going to matter, right? It's always going to look like this on large scales up to some order 1 factor. So it's mostly convention. Anything else? All right. So we can write down some new force like this. You can probably write down other forces if you want, but this is a fairly common one. People have constrained these kinds of forces before. And so here, on the y-axis, right, so this is strength relative to gravity, and on the x-axis is range. And I should have maybe emphasized this earlier, but when I say long range, I do mean long range in this talk, right? So this is 1 parsec. Here's a gigaparsec. On the left edge, we're down to a microparsec. These are very much astrophysical ranges. These are long-range interactions. Although, as I'll emphasize later, actually, some of this does extend well to the left. The probably best known constraint on dark matter self-interactions that you're likely all familiar with comes from the Bullet cluster. And the Bullet cluster is this pair of 2 clusters of galaxies that we know have recently collided. and the dark matter in these two clusters pass through one another. Right? So we see the dark matter now on the opposite side of each cluster from where it was before. The fact that the dark matter went through itself in that way tells you that it can't interact too strongly with itself, or else it would have gone flying off in every direction, or if there's some dissipation, it would have been stuck in the center. But in any case, it wouldn't have passed through like that. And so this is the sort of conventional constraint that's set on dark matter self-interactions. We'll talk about some caveats related to it pretty soon. But that's plotted here for different dark matter masses. And the reason I'm plotting it for two different dark matter masses is that this constraint, when described in strength relative to gravity, depends on the dark matter mass. Again, we'll sort of come back to this point. The only thing I want to emphasize here now is that this lower line, right, corresponds to dark matter with a mass of 10 to the minus 10 solar masses. Actually, if you're familiar with constraints on PBH dark matter, you'll know that this is already excluded, in fact. You can't have dark matter entirely at this mass. I think the limit right now is about 10 to the minus 12. That being said, you can try and get around this to some extent with distributions. The point, though, is that, roughly speaking, this is the heaviest dark matter that you could possibly have. Okay, there's some subtleties, but broadly speaking. The next line up is 10 orders of magnitude lighter, but that's still 10 to the minus 20 solar masses. This is still very, very heavy dark matter, right? If you were to talk about something like GeV dark matter, the corresponding line would be way off this plot. I don't remember exactly where it is. I think it's like 10 to the 37 or something. The point is, it's much, much higher.
I think for GeV, it's like a strong cross section, like a strong.
Yeah, no, that's exactly right. Yeah.
Right?
So the constraint, again, I'll show the numbers later, but it's about a centimeter squared per gram. Yeah. The point, though, is these lines are very dependent on your dark matter mass, and so depending on your dark matter model, you can have huge amounts of parameter space well above this, in fact. That'll matter a little bit later on. At very long ranges, there are a couple other constraints that people have set. So one of them, above a megaparsec, here comes from observations of galaxy cluster, measurements of masses in galaxy clusters. I'll explain this later, so I don't want to get into it now. The other one comes from observations of tidal tails of dwarves in the Milky Way. Again, I'll explain both these constraints later on. The main thing I want to emphasize at this point, though, is that there's this big parameter space at these sort of finite ranges and strengths well above gravity that isn't currently constrained. And this parameter space can have pretty massive effects. We'll sort of see this later on, but for example, you can be sitting in places in this parameter space that will, one second, yeah.
That was the reason I can't.
Never mind. You can be sitting in places in this parameter space that would dramatically alter the velocity distribution of dark matter in the Milky Way. Right? We normally assume that dark matter has a local virial velocity of whatever, 10 to the minus 2, right, in our vicinity. But in the presence of new forces, you could dramatically change that. You could have dark matter that's a lot faster or a lot slower. Okay. So lots of parameter space. We're going to try and fill in some of the space off to the left. The main way that I'm going to do that in this talk is using the bullet cluster, but now using it in a different way. But one point that I want to make early on is that really this bullet cluster story that I'm going to tell you is meant in some sense as an old sort of example. And actually there's a more general point we're making that we think can apply to a lot of astrophysical systems, and some of them can probably set even stronger constraints than the bullet cluster, and we're thinking about some of those now. I'll come back to this. But the bullet cluster is a nice concrete example for understanding this. So here are some pictures of it. On the left we have optical images, which are the black splotches. Those are stars, and then we have mass contours inferred from gravitational lensing. On the right, still the gravitational lensing contours, and then X-ray observations of the gas between these clusters. And there's a few things I want to highlight here. So, first off, just some naming conventions, right? So there's two clusters. There's a big one, and there's a small one. The big one turns out to be about 10 times bigger across, about 10 times heavier. It has about 10 times less central density, roughly speaking. I'm going to call that one the A cluster. I'm going to call the little one the B cluster, just for future reference. The little one's also sometimes called the actual bullet of the bullet cluster. What are we observing here? So the mass contours are overwhelmingly from dark matter, right? These things are dark matter dominated. I think they're more than 90% dark matter. I forget exactly what fraction. The big one is about a megaparsec across. The little one's about 10 times smaller again, so about 100 kiloparsecs. That'll matter. That's going to set the sort of ranges at which these effects matter. And as I was saying earlier, right, when we observe these things, we see that the dark matter is well separated. You can measure where the stars are, and you can measure a centroid for the star positions, and it turns out to match the dark matter positions pretty well. Whereas when you look at the gas, you can see immediately that it's located in the center. And the one other thing that you can see about the gas is that there are these really noticeable, especially on the right, triangular patterns. These are shock waves because the gas collided supersonically. Again, that's going to matter later on. Okay. So first off, I keep talking about this conventional bullet cluster constraint, right? That comes just from making sure that dark matter passes through itself and doesn't fly off in every direction. So conventionally, this is done for hard sphere scattering, as you get for something like strong force scattering. And then you get a constraint of cross-section no more than 1 centimeter squared per gram of mass of the dark matter particle. You can extend this to other kinds of scattering, including longer range scattering, and roughly speaking, you can just replace this cross-section with a momentum transfer cross-section, which is weighted by the fractional momentum transfer in your scattering. That being said, this is already not exactly right, and in particular this assumes that you're not too dominated by very soft scattering. I'll sort of talk about why soon enough. So what's the problem with hard scattering for the kinds of forces that we're going to look at? Well, the problem is that these calculations that I just showed, including the momentum transfer version, they assume one-on-one particle scattering. You have one dark matter particle that flies in, it scatters from one particle in the other cluster, it flies off in some new direction. That's just not the right way to think about this. Once the range of your new force is larger than the inner particle spacing. Because once this is the case, you can have scattering events in which the impact parameter, right, the distance of closest approach between particles, is substantially larger than the space between particles, and then you're actually seeing many particles at once. Right? So I sort of illustrated this off to the right. When your range is sufficiently short, sure, you pass by a single particle, you interact with it, everything's fine. But once ranges are long, at the point that you claim you're interacting with a particular particle and you have some impact parameter that's still smaller than your range, right? So this is an allowed interaction. In reality, there are a whole bunch of other particles that are closer to you. So, in principle, if you want to, you can still take this kind of force and you can calculate a traditional bullet cluster constraint format. And the way that you can do this is that you just restrict to hard scattering events, right? You restrict to small impact parameters where you get a large momentum transfer, and you can restrict your impact parameters that are small enough that everything holds up. That's a thing you can do, and you'll get constraints, and in fact, when I plotted the lines earlier, that's what I did. But you're really throwing out a large fraction of the effect, right? Because in practice, at these long ranges, you do get a lot of scattering from large impact parameters and just weak scattering. So you might try and include that, right? You might try and sum over these soft scattering events. But now you run into a different problem, which is that really the whole picture that I told from the beginning, where dark matter flies off in different directions because of scattering, just doesn't apply anymore. If you have really long-range scattering, you're really just moving through some classical potential, and two dark matter particles that come in next to each other are going to come out next to each other because they see roughly the same potential up to some small gradients. And so you can't think about this constraint in the same way once you're in the soft scattering limit. This isn't what happens, right? Dark matter doesn't go flying off. One way that you can think about it, a better way, is the process of dynamical friction. And so this is something you might have heard about. I'll explain how it works, though, for anyone who hasn't. Dynamical friction is a friction-like process, in some sense, that transfers energy from some object to a fluid around it when they interact. And if you imagine, for example, some object, let's say some star. This is an example that'll matter in the second half of the talk. We'll use it now for simplicity. You have some star moving through a dark matter background. And they interact just gravitationally, right? Forget about any new interactions. So if your star was just sitting in place, it would slowly pull in dark matter, and you would end up with a dark matter overdensity around the star compared to this general background density. But if your star is moving, that dark matter tends to fall in behind it, right? Because it takes time for the dark matter to fall in, and the star used to be over here, so the dark matter ends up behind it. Now there's an overdensity of dark matter behind the star, relative to in front of it, and so there's a tendency for the dark matter to pull, on average, on the star backwards, and that's going to slow down your star, and it's going to slowly speed up your dark matter, so there's a transfer of energy here. That's dynamical friction. To be a little bit more quantitative about it, you get some acceleration on an object, and now let's go ahead and come back to our bullet cluster example, just for concreteness. So you have some object B, right, the B cluster, the little one, and it's moving through the background of the large cluster. And it gets some acceleration that has, okay, some order 1 factors we don't care about too much. And now you'll notice it has the coupling squared. Why is it the coupling squared? Well, it's because, again, first there's 1 power of the coupling from pulling stuff in, and then there's a second one from the dark matter pulling back on your star or on the B cluster. Right? So you go as force of gravity or force of your new force squared. You increase with the mass of the object, or of the B cluster. This is actually a really unintuitive thing, right? That your acceleration increases with mass because the force rises with mass so much. But again, that's just this effect again, where there's 2 powers of mass in how large the force is, and then in the acceleration you get 1 power of the mass back. Then you care about the density of the background. That shouldn't be surprising, right? The more stuff there is around you, the more this effect can happen. There's some velocity dependence, and there's some logarithmic factors that hide, for example, the force range, and so on. They don't matter for us too much. For those of you that are more familiar with dynamical friction, I'll point out that, so here we're in a regime where you fall off with the velocity of the object squared. You might know that that's not always the case, but the thing to keep in mind here is that, again, the B cluster is falling in from infinity, so it's moving with at least the escape velocity of an object in the A cluster. That's necessarily larger than the velocity of things that are in the A cluster, because if they were moving faster, they would have escaped. So we are comfortably in this regime. If you don't know what I'm talking about, don't worry about it too much. The point is you fall off with velocity in this way, and again, it's not hard to see why, right? At larger velocities, you spend less time here, and the stuff ends up farther behind you.
Sorry, are those 2 V's? It's bugging me that you have VB over VB cubed.
Oh, got it. Sorry, this is a vector, right? So this is, strictly speaking, this sets you a direction. So you're going as 1 over V squared.
Okay,
Yeah.
I understand.
Sorry. No, that might be a little
no,
more
I got it.
Yeah. Good. So this will happen in the bullet cluster, right? The little B cluster will fall through the A cluster, and it'll get slowed down by the fact that there's a background dark matter in the A cluster that you're interacting with gravitationally or through a new force. That being said, you can sit down and you can work out how large this effect is, and you'll find that the change in the velocity of the B cluster is no more than about 4%, which isn't remotely observable. And when I say that it's no more than about 4%, I really mean it. This is true for all couplings, even very large ones. The reason being that this effect actually turns out to be asymptotically independent of the strength of your new force. And the reason for this is exactly this dependence on the velocity square, where due to a different effect that we'll get to in a second, at large couplings you speed up the B cluster, and then you reduce dynamical friction. The point for now, though, is that dynamical friction is a really small effect, right? No matter what you do, you're not changing the B cluster velocity very much, and we can't constrain that velocity at a 4% level, at least not in any way that we've thought of. So we don't think that you can constrain new forces based on this effect. But as I was just alluding to, there's really a bigger effect here, which is that in the presence of this kind of new force, you're going to speed up the B cluster a lot more. Well, speed it up or slow it down, depending on whether you're attractive or repulsive. Right? And the reason for that is that you're just directly changing the potential of particles in the B cluster in the vicinity of the A cluster, right? You've changed gravity in some sense. I'll note at this point, by the way, that for the next while, I'm going to specialize to attractive dark matter forces, right? So dark matter that always attracts itself. The reason for this is just that in the repulsive case, there are stronger constraints you can set in a different way that I'll get to later. So for now, let's focus on attractive forces. Yeah?
So is it, I mean, naively I would have thought that for these kinds of bullet cluster things, gravity is not important at all. So if you say, but you're going to probably get to that, right? I mean,
well, no. So gravity is significant. Gravity is, roughly speaking, why the two collided. That's not fully true, right? I mean, they had some initial conditions. They were roughly lined up towards each other. But no, the dominant contribution to the velocity of the bullet cluster components at the time of collision was, in fact, gravity.
sure, but that was before they collided. That's just as well as like how far they fell from or something
Yes.
like that, right?
Sure, yeah.
Yeah, but I guess, okay, well, why don't you go on? I'm curious to see how I mean, it's just my intuition would be that while they're colliding, right, it's not,
Oh, good,
not
good,
very
good.
important.
That's
Yeah.
exactly right.
But that's because, you know, how fast they're colliding is, I would think, for practical purposes, an initial condition that we don't know.
So that's okay, good.
But
So
maybe
you're
that's-
completely
maybe
right that during the collision, gravity doesn't
Right.
matter too much.
Ah.
I don't know exactly how much it matters, honestly, but it won't matter for this at least.
Okay.
We're going to talk about the infall itself, where it does matter.
There it is.
And it's not quite an initial conditions problem,
Okay.
although you're not entirely wrong, and we'll get to that.
Okay, good.
Yes. Good. Right. Oh, yeah.
What
one
is
question.
an FW again?
Why am I using an NFW profile in this plot?
No, what does NFW stand for?
Oh, Navarro-Frank-White. It's three names.
It's the standard parameterization of what a dark matter halo looks like as a function of radius. It matches what is seen it pretty much matches what is seen in simulations.
And it was derived theoretically for simple dark matter.
Well, derived, written down.
Yeah, so, okay, we'll get to this plot in a second, but yeah, I use NFW profiles a lot in this talk as just sort of a classic example of a dark matter profile. Generally speaking, and I'll try to emphasize this later, our results don't really depend on the profile very much. I'll show some dependence later on. Although there will be an exception to that in just a second. Okay, good. So as we were just discussing, right, so why do these clusters collide? They collide because they've fallen from infinity due to gravity. And so you can talk about some potential of the particles in the little b cluster with respect to the a cluster. And so here on the right, I've plotted what that potential looks like in some arbitrary units. We're just looking for a shape here. For an NFW profile, that's this blue line with just gravity. Right? So this is, well, it's some 1 over r potential at large radii, and then at smaller radii. It's not that because you have some profile, but nonetheless. If we now introduce a new infinite range force, right, with strength, let's say, equal to gravity, we're obviously going to change this. So for example, here the yellow, orange, whatever color you prefer line at the bottom is a force with strength equal to gravity, and I've even done a finite range, but it's a finite range of 10 times the scale radius of the A cluster. Sorry, I should have been clear, by the way. So this is the radius in units of the scale radius, right, a characteristic length scale of the A cluster. That's r star. And so when your force is much longer ranged than that characteristic size, you've basically just increased gravity by a factor of 2. Right? This isn't like a deep insightful thing, right? The force is essentially gravity. But what about finite range forces? So I've shown that here for two strengths, both at a range of, let's say, 1/100th the scale radius. And the green line is 1,000 times stronger than gravity. And yet you'll notice that essentially the potential is unchanged, and it starts to change just a little bit at very short ranges. In fact, even this significant deviation is a property of NFW profiles, which happen to be very sharply peaked at small radii. If you use a profile that's less cuspy, you wouldn't even find this. You'd find that there really isn't a meaningful deviation at any radius. In the red line, I've plotted this now at 10 times stronger coupling, so 10 to the 4 times. And now you'll start to see that even at multiple scale radii, you start to see some change in the potential seen by this particle. There's a reason I'm showing these two strengths, which is that I want to start emphasizing from here that roughly speaking, you're going to want to see significant effects. You're going to want to look at couplings that are roughly, let's say, r star over lambda squared. Right? So here r star is 100 times lambda, and so you need a coupling that's roughly 100 squared times gravity in order to see an order 1 effect at radii greater than 1. Now you might say, wait a second, you do have significant effects at very small radii, even for the smaller coupling here. Why can't you look for some effect of that? As I was emphasizing, though, this is a result of NFW profile specifically. We don't actually know that this is an accurate description of the profile at small radii. We shouldn't trust that. And so we're going to try and set constraints using only physics at larger radii during the infall. Right? At very small radii, as you said, gravity doesn't affect the collision very much. Probably this wouldn't either. And in any case, we can't trust this line because we just don't know what's happening in the center that well. We want to look at just the physics at long ranges. Okay. So in principle, at least, right, some new force can change the potential, and therefore it can change the way that the bullet cluster collides. Naively, and people have made this mistake before, you might say that, okay, well, when your clusters are order a megaparsec apart, if you have some force with range, let's say a kiloparsec, you have an exponential suppression. That suppression is going to be something like e to the minus a megaparsec over a kiloparsec. That's e to the minus 1,000. You're not going to get anything meaningful. Right? So it'd be some ridiculous suppression, and you could never constrain new forces in this way. I've sort of already given away that this isn't right, though, because I just showed you potentials in which it is modified in this regime. And the reason for this is that actually, in the presence of realistic dark matter profiles, which have some smooth gradient that extends even to large radii, this suppression goes from an exponential to a power law. Right? And so I want to explain where that arises from. So here on the left, right, let's just imagine this is the A cluster, right? It has some dark matter profile. There's more dark matter in the center, less on the outside. And we're looking at some example dark matter particle that's located somewhere inside that halo. And then we have some new force with the range lambda. That range lambda, again, is a lot smaller than the characteristic size of A. If we look at the dark matter distribution around this little particle, on average, there's going to be a little bit more density. Right? So here's density as a function of radius. A little bit more dark matter density towards the center than away from the center, simply because the dark matter density in the center is higher. And that difference in the masses ahead and behind it is going to lead to some net force. Very roughly, just to get the parametrics, right? You can imagine that the force from the part that's out is, okay, alpha g, right, is strength, times the amount of mass over lambda squared, minus, okay, the same thing for the mass that's interior of the particle. How large are those masses? Okay, they're about the local dark matter density times the range of the force cubed, just as a characteristic volume. And the entire effect comes from the contrast in the density between the outside part and the inside part. Well, how big is that density? Okay, fractionally, it's going to be something like lambda over r star. Right? It's going to be roughly the size of this over whatever the characteristic length scale of your cluster is, and we've just called that r star. And this will be true for a wide variety of profiles, right? Very generically, if you have a length scale r star, you should expect this kind of gradient. Again, this actually breaks down in the very center of NFW profiles, but at finite radii, or at significant radii, it's perfectly fine. And even for NFW profiles, you just get a larger effect. Right? So the result of this is that very generically, right, just in the presence of these kinds of gradients, you get a new force that looks like a strength times a density, and then times lambda squared over r star. And it's that lambda squared that I want to emphasize, right? That you're falling off again as the second power of lambda instead of exponentially as e to the minus some constant over lambda. This is what's going to allow us to set meaningful constraints even at finite ranges. Okay, questions here? Okay.
So just the physical picture, sorry, just catching up. The physical picture is you're sort of imagining, you're comparing the force from a shell of the inside, which is order lambda, and then outside, because the range is order lambda, it's sort of a shell of thickness lambda around that, or?
I mean, I would think of it as half spheres, but if you want to, I mean, you can think of all the stuff that's order lambda away.
Okay, sorry, I see, yeah.
But the volume's order lambda cubed, right?
Right.
Yeah.
Okay, and, I see.
No, okay, you might say, wait a second, you know, I'm going over lambda squared here, but you can check, right? So there's more stuff at larger radii, and so you're dominated by larger radii.
Sure. Okay, no, okay, I understand. Okay, so it's sort of, yeah, it's the density is a little bit larger there, and you're saying that's, okay, I got it, thanks.
Other questions? Okay. Yeah, so we've seen that we get some new force, right? It's only power law suppressed. What will this actually do? So broadly speaking, there's two different ways that this could modify the bullet cluster collision. And which one happens is going to depend on whether dark matter and the standard model in each of the clusters, but especially in the B cluster, stays together. You could have a regime where the dark matter is ripped away, right? And that'll lead to some observable effects. Or you could have one in which the standard model stays with it. We're going to be able to constrain both. And I'll talk about which one we expect to happen later on. Okay, so let's start with the situation in which dark matter and the standard model separate. Right. Well, as I sort of alluded to earlier, we've measured the positions of the dark matter now, right, after the collision. We've also measured the centroids of the star mass. And these match up. They match up to, okay, order tens of kiloparsecs, a lot less than the size of either of the clusters. So this just immediately tells you that this regime can't really have happened, right? You can't have had the stars ripped away from the B cluster, because even now, they're quite a bit less than the B cluster size away from the center of it.
Can you remind me, what is the size of the big one again?
Yeah, so this is order a megaparsec, this is order 100 kiloparsecs.
That's right.
Right. Now, one thing that people sometimes ask about is, wait a second, you have some new attractive force. As the B cluster is falling in, actually I guess it's falling in from this side, let's say. As the B cluster is falling in, your new force causes the dark matter to get pulled, and so it gets accelerated more, it ends up ahead. But then on the other side, right, and now you're well on the other side, the dark matter is getting pulled backwards, so it'll get slowed down. And shouldn't these effects cancel? Notice, however, that these effects cancel in terms of velocity, but not position, right? The potential of particles in B is always, or dark matter particles in B is always deeper, right? They're always moving at least as fast as the standard model, and in the vicinity of the A cluster, they're moving faster. Right? Sure, the velocity is now slowed down, but the position continues to be different. And so this effect does persist even for a purely attractive force. What kind of constraint? Oh yeah, go ahead.
So, out of curiosity, what's the time scale of this fully calculation?
Good.
Billion
It's it is order billion years.
There's no way we can observe a complete event. Or,
That's right. So we don't get to observe dynamics in this. We just observe the final state. Yeah. That's right. Okay, so what kind of constraint can you set from this? Very roughly, just for sort of order of magnitude estimates, and then we've done this more carefully numerically. You can check that this constraint comes down to making sure that the potential of dark matter particles at the scale radius of A, right, so at a megaparsec, has not been modified by more than order unity, right? You've changed that potential by less than order 1.
By the way, you should, you can use this nice thing, there's this elementary physics thing of like if you swim downstream and then swim upstream versus no current, which way is faster, and naively you might think they would be the same, but they're not because of exactly this kind of.
So this effect
It's
is
not
actually
exactly
this effect's
the same.
actually even larger than that because the dark matter, the velocity's always been larger. The dark matter's never been
Yeah,
going slower.
and I'm just saying,
But
that
yeah.
it's just the velocity versus position thing,
Yeah,
right?
yeah.
Yeah.
Okay. What does that correspond to? Well, at infinite ranges, it's certainly going to mean that we can't have new forces stronger than basically gravity, right? That would change this velocity by order 1, I guess square root 2. And then at shorter ranges, as I've emphasized before, you fall off as lambda the minus second, right? As the ratio of the scale radius to lambda squared, because that's the suppression of this kind of force. So broadly speaking, that's the kind of constraint we're going to get, and again, you can work this out more carefully numerically. Fine. That's the separation case, where dark matter and the standard model separate.
So is there really so do you really mean much less than, or do you really, is there a number associated with that, or is that
So
an
what-
accuracy number or something?
What I'll get to in a second is that the other case, you get marginally weaker constraints. The difference is order 1 numbers. The result of that is that I'm not really going to worry too much about exactly what the order 1 constraint you should set here is, because we're going to use the more conservative of the two cases, which is the next one. Yeah, I mean, what should I say? Yeah, I mean, okay, this claim corresponds to requiring this to be less than d of r star.
Okay.
In reality, again, what you should actually do is you should simulate the infall, you should see exactly what the position difference is, and you should see if it matches what we've observed. Fine. But for an order of magnitude estimate,
So
let's say
somehow
1.
it's like the statement that 25 kiloparsec is a lot smaller, there's basically no effect to a very high accuracy,
Yeah.
and that's what's making that number small.
Yeah.
But to really be quantitative, you'd need to simulate that.
Yeah. And in fact, I'm being a little bit conservative here, so this again is order 100 kiloparsecs, so you might say that this isn't that much smaller. But actually, if you really did modify the potential by order 1, the separation you get isn't order of the B cluster size, it's order of the A cluster size, because that's the distance over which you've moved. That's 10 times larger, so it really is much, much less than the characteristic displacement.
Okay.
The point of this being much less than, or being somewhat less than the B cluster size, though, is just that they can't have been slightly ripped away. That's not a possibility, right? It hasn't been ripped away at all. Good. This is the situation that we mostly expect in the parameter space will consider, although it's borderline at the very smallest couplings we can constrain, unless there's new dark matter standard model interactions. New dark matter standard model interactions could cause the B cluster to stay together, because there's now something more strongly binding standard model to it. So it's still interesting to consider the alternate case, although this is likely the more generic one. Again, though, we'll be conservative and we'll look at the slightly weaker constraints on the second case. So what do you do if dark matter and the standard model separate? After all, don't separate, right? Well, the reason that you can still constrain this regime is that there's non-trivial gas dynamics that happen in the collision. So these are some simulations people have done.
Sorry, I've lost track. What question you were asking now? You're saying you're looking at some case. I'm sorry, because here this seemed pretty clear, but now you're looking at some other situation?
Yeah. So this is a constraint you can set on the assumption that the D cluster stars and dark matter were separated. And so we just set some constraint based on whether or not they did. But suppose that you have some new force, for example, that's going to keep them bound together, right? Such that the attraction of the standard model to the to the B cluster itself matters.
So now you're
And
adding
now this
some
story
magic
doesn't hold
force
up.
that's sticking them together.
Yeah, and so now this story doesn't hold up because it doesn't really, you might imagine that, okay, the dark matter gets a little bit ahead of the standard model as it's falling in due to the new force, but now the dark matter of the B cluster is ahead of its stars. It pulls the stars along, and so because of that, the stars pass through at the same speed.
But, sorry, I'm still confused. The whole point of the bullet cluster was that the stars, that's right. The stars went through with the dark matter. It's the gas that
Yeah.
was left in the right.
Yes, no,
Okay.
good.
Yep.
But you could try and imagine a universe in which the stars get pulled along with it, and then this story falls apart. So that's why we're considering a second case,
Okay.
right? What if the stars get pulled along with it? Well, the problem is that if the stars get pulled along with it, you expect the gas to also be pulled along with it. I mean, you could try and do some crazy model building in which they interact very differently, but generically, if the dark matter is interacting with the standard model sufficiently, it's interacting with it sufficiently. And there's gas dynamics that happen in the bullet cluster, right? I mentioned these shock waves earlier that you can see between the two clusters. You can also see them in simulations, just of the gas, as again, the bullet falls through the other cluster. And the opening angle of this cone that forms here, or that you can see in the picture earlier, that opening angle depends on the velocity of the gas, right? It depends on its Mach number. So sort of the usual, supersonic, sonic boom cone shape. Okay, it's a little more complicated here, but that's the broad picture. And so based on our observations of the opening angle of that cone, we can determine how quickly the gas collided. It turns out that if you measure the speed of the collision of that gas from these observations, you get something of order, 2,900 kilometers per second. We can also predict, though, what the collision speed should be for two clusters that just fell in from infinity. And it turns out that it's about 1,900 kilometers per second, but with substantial uncertainties. Where are these uncertainties coming from? They're coming mainly from initial conditions. You were asking about this earlier, right? So the main thing we don't know is we don't know how quickly these clusters were moving at the beginning. There's also inevitably there's some uncertainties in the simulations. I couldn't find these anywhere, and it doesn't really matter for our purposes, but presumably there's some uncertainty there too. Fine. Oh, yeah, go ahead.
There's another fuzziness in this problem, and that's the unstated assumption that we're looking in the collision plane.
That's right. Good. So there's some uncertainty from that. There is some observational evidence that we're looking pretty nicely that way. It has been long enough since I've read about this that I'm blanking how it is, but I can find it for you afterwards if you ask me. We do have some reason to believe that we are actually
Redshifts
looking.
of the component galaxies, but there are not many of them.
Okay, so I'm sure there's some order 1 uncertainties. All I'm really going to assume, again, for the constraints here, is that these numbers match up to order 1. And so I think that's fairly solid. That shouldn't change, but yeah, there's some uncertainty associated with that.
If it was at an oblique angle, then it would be going even faster than what we apparently
Yes.
observed, right?
Yeah.
So what would that, I would somehow guess that would make the constraints.
You're right. That would okay, good. So that would make this discrepancy larger, which is a little bit awkward. So speaking of this discrepancy, actually up until order 10 years ago, there were occasional claims that this discrepancy actually indicated that there were new long-range dark matter self-interactions to make these numbers match up. More recent simulations have increased uncertainties, so again, I think now these things match to whatever it is, about 1.5 sigma, even not including any simulation uncertainty. So now they match fairly well. But yeah, I mean, if you were looking at a sharper angle, the discrepancy would increase, and we'd start to be confused again about how quickly these these clusters had to be moving while they were still far apart. Okay, so again, right, so we can require that the collision velocity of the gas not change by more than order 1. And again, up to order 1 factors, this is exactly the same constraint, that you don't change the potential at the scale radius by more than an order 1 factor, leading to the same kind of constraint. Again, in reality, what we do is we numerically simulate how this infall happens, and we make sure that the velocity isn't changed by more than order 1. But you could sort of immediately see roughly what the constraint should look like. Okay, so in both situations, we can set a constraint. Up to order 1 factors, it's the same constraint. In practice, this one's a little bit weaker, but it's not a large difference. Good. Now, I said earlier that I'm focusing on attractive forces here, right, for which I've set the constraint in the bottom right. Why not repulsive forces? Well, for repulsive forces, there's a much easier way to set a constraint, which is that ultrafaint dwarfs exist. So ultrafaint dwarfs, very small galaxies, we'll come back to these later, they're going to matter. Ooh, I'm running way behind on time, sorry. Well, I will quickly talk about ultrafaint dwarfs a little bit later. Ultrafaint dwarfs are very small galaxies that have dark matter halos that we think are order kiloparsec across. Actually, the uncertainties here are rather substantial, but roughly speaking, let's say they're a kiloparsec across. And the fact that halos of that size exist tells you that you can't have, for example, a new repulsive force stronger than gravity with range greater than a kiloparsec, because your dark matter would just push itself apart instead of binding together. We can extend this to finite ranges in essentially the same way, right? We check that the net force on dark matter particles is still inward, and the constraint you get is going to look a lot like the one from before, still with this lambda to the -2nd suppression. But now the characteristic size isn't a megaparsec like it was in the Bullet cluster, it's a kiloparsec, because this is a much smaller system. So, okay, we can set constraints on repulsive forces that look broadly the same way, but they extend to shorter ranges. Very straightforward. There are various other things we can try to do. Given how far behind on time I am, let me go ahead and skip some of these other constraints. You can ask me about them afterwards, and I'll just go ahead and plot our results and then try and say a few things about interactions with the standard model. So here's that plot from the beginning, right? With the existing constraints, so from the Bullet cluster and from these other things I didn't have time to talk about. And now I've plotted in colors the new constraints that we're talking about. And by the way, actually, I should have emphasized this earlier. All of these constraints have been used before in the infinite range case. People haven't worked out how they work in the finite range, at finite ranges. But I don't want to make it sound like we completely invented these. They've been done before in infinite ranges. Here, the green line and the green shaded region corresponds to, again, the more conservative of the two cases, so the collision velocity of the gas, done for an NFW profile, which is a sort of classic example. And there I'm, right, and assuming a collision at order the scale radius. I've illustratively plotted a couple other lines here. So the blue line is, okay, what if it's not an NFW profile? What if it's something like a King profile? Actually, it turns out that the Bullet cluster is, the lensing measurements of the Bullet cluster are fit a little bit better by a King profile. Fine. King profiles are slightly less cuspy in the center. You get some slightly stronger constraint, but it's not a big change. If we instead assume that the collision happens at larger radii, so we really want to exclude all the dynamics at small radii, we can do this at 2 scale radii instead of 1 scale radius, and then you get the red line. Again, not a very big change, and that's sort of my point, right? This line can vary a little bit with your detailed assumptions, but basically you're going to get the same. You're going to get the same result no matter what. And your takeaway here should be that, again, there's a lot of parameter space here for which this is, which was not previously excluded. At the very least, right, this sort of triangle here below the very heavy dark matter line, right, for all dark matter, this is new parameter space that's being excluded. But again, remember that if you have GeV scale dark matter, these lines are way, way up there. And so now you can set stronger constraints down to something like, I think, order centimeter type separations, right? So much, much shorter range forces than here. The only reason I'm not plotting that is because otherwise all of this gets ridiculously small and you can't see anything. So there's a lot of parameter space for which you can do much better than incoherent Bullet cluster scattering, right? Roughly speaking, once your force range is larger than interparticle spacing, and for GeV scale dark matter, the separation is order centimeters. Once your range is larger than interparticle spacing, you can get stronger constraints using comparisons like this. Okay, so this is attractive forces. I should have been clear about that. On the right, again, is repulsive forces. And here, all right, I'm just plotting the one constraint because it's better than everything else, which is from ultrafaint dwarfs. Again, there's some uncertainty here because we don't know that much about ultrafaint dwarf halo sizes, but it's not going to change things dramatically. Great. That's the dark matter self-interaction part of this that ended up taking almost all of my time. Questions about that before I talk a little bit about interactions with the standard model? Okay. What do I want to say about interactions with the standard model in 10 minutes? So we can talk about interactions between dark matter and the standard model that still look like Yukawa forces. Again, it doesn't matter too much. This is just a nice example. The main thing that I want to emphasize here, though, is that now the potential that you look at has some effective strength relative to gravity, right? Alpha ST between standard model and the dark matter. that's given just by a geometric mean of the dark matter only coupling and the standard model only one. Right? And this happens because, really at an interaction level, there's some coupling to a standard model particle, some coupling to a dark matter particle, and you're going to look at the product of the two. This is going to matter a lot because actually all of the current strongest constraints on these kinds of forces come simply from a constraint on the standard model side and a constraint on the dark matter side. You're just going to look at the geometric mean of those constraints. There are constraints on this directly. Given time, I'm not going to try and talk about it. It's currently subdominant at all ranges. We, however, are going to set a new constraint in precisely this cross-coupling. And then from here, again, you depend on the masses of particles and you have some finite range. The one other thing I'll emphasize is that unlike the first half of this talk, I'm no longer assuming that your dark matter has a net charge. Right? This part of the talk works even for dark matter that is, let's say, millicharged and has mixed charges. The thing that we require, though, is that the standard model matter, that stars in particular, still have a net charge. That's not a crazy thing. If you do something like gauge B minus L, stars have a non-zero baryon minus lepton number, so they're going to have a large net charge. That's perfectly fine. Your dark matter can be net neutral. I just showed you what the dark matter constraints are, right? What the constraints on this are. What about the constraints on the standard model side? So these depend a lot on how much your new force looks like gravity. So generically, if you write down some crazy new force that looks nothing at all like gravity, and by looks nothing at all like gravity, I mean that it couples to particles in a way that's not at all proportional to their mass. You can set some constraint that's going to sit down here. And you set this using the microscope experiment, which is a satellite in orbit around Earth with two concentric cylinders made of different alloys. And we look for changes, or for differences in the acceleration of these two cylinders in the gravitational potential of the Earth. Right? That, since the radius of this orbit is a lot smaller than all of these ranges, this is all effectively infinite range. You're just talking about some equivalence principle violating effect. And so depending on exactly how EP violating you are, you'll get some constraint down here. I think for order 1 EP violation, it's something like 10 to the minus 15, in fact. But that's sort of crazy. It's very hard to write down a model in which that'll happen. Here, I've assumed 1 or 2 orders of magnitude weaker than that. Okay, so this is in the case of being very much EP violating. In the limit where you really look just like gravity, right? So you really couple in a way that's proportional to mass, and people try to write down scalar gravity models that do this. You get this much weaker constraint up here, and the reason for this is that we don't really know how to look for these kinds of weak long-range forces when they look just like gravity. Right? All you can do now is you can look for deviations from the 1 over r potential of gravity, but when you're looking at objects that are much closer together than lambda, that's e to the minus r over lambda is basically 1, and so this is very weak. So it's hard to do this at long ranges. That's also why you see that it gets weaker and weaker as you go to longer ranges, because again, you have less and less effect of this exponential, you really start to look just like gravity. I've cut this off at around 1 times gravity, because going above this starts to become a little bit nonsensical. Even scalar gravity models will not give you the correct amount of, for example, lensing of light in gravitational potentials. Really, we can even probably constrain that a little bit lower. The point is that this is sort of a model building upper bound, and even this is very generous. It's very, very hard to build models that are actually the CP preserving. Almost any model is going to be sitting a lot closer to the green line. But these are kind of the extremes, right? Like you expect to be sitting probably somewhere between these lines for a new interaction of the standard model. So you can combine these kinds of lines with the dark matter only constraints I showed before. I don't think we need to dwell on this plot given time, but again, right, so in green I'm always going to have things that are very EP violating, in blue things that are very EP preserving, and then depending on the mass of your dark matter and depending on whether forces are attractive or repulsive, you'll get slightly different constraints. Fine. Okay, so what did we do? Right, that's the actual new part here. So we're going to look again at dynamical friction. Luckily I explained what this is earlier. Now we're going to look at dynamical friction of stars in a dark matter halo. Right? So as a star moves through a dark matter halo, even with just gravity, it's going to slowly give energy to that halo, and the star is going to slow down. This is actually how galaxies, in some sense, gravitationally thermalize. Right? So you can think about stars in a galaxy as being atoms in a gas, and then they have some velocity, and you can associate a temperature with that. And if your dark matter is light, right, if you have GeV dark matter, right, not PVHs, then for realistic dark matter velocities, the dark matter is much, much, much colder. And we know that that can't last forever, right? This has to eventually thermalize. The stars have to end up at the same temperature as the dark matter. And dynamical friction is exactly how that happens. Why do we not normally hear about this? We don't normally hear about this because even in the ultrafaint dwarfs that we talk about where this effect is optimized, this process takes many, many times the age of the universe. And we'll get to that in a second. Good. So what's an ultrafaint dwarf? As I said, these are these very small galaxies. Here's an example of one, Segue 1. This is the one we used. It's the really obvious galaxy in the center. If you can't see it, don't worry, I can't either. There are other images where it's a little easier to see. What do we know about Segue 1? We know that it's very small. Again, it has a scale radius, if you think of order kiloparsecs. It's old, and we know this from metallicity measurements of the stars in it. We think actually it's about 12 billion years old. I'm going to conservatively say 10, but it doesn't really matter.
So
We're doing the order of
what's
magnitude.
the basic reason why small halos are better for this effect?
Okay, good, yeah. So it's a little bit tricky. If we forget about velocities for a second, you want high dark matter densities, right? Dynamical friction is going to increase with dark matter density. Ultrafaint dwarfs have very high dark matter densities, much larger than anything that's accessible in a large galaxy. I don't want to say that it's larger than anything you can get in the Milky Way, right? We don't really know what the dark matter density is in the very center of the Milky Way, but we can't measure things there. But in an ultrafaint dwarf, we can measure nicely, right? Star behavior in areas that have a dark matter density of order a solar mass per cubic parsec, that's 4 or 5 orders of magnitude larger than what's typical in a spiral galaxy.
And why is that in turn? Like, why are they so much more dense? Do we know? Just simulations, or do we have a understanding of that?
I don't know if I have a quick intuition for why structure formation should end that way.
Is it predicted by Lagrangian?
As far as I know, this matches reasonably well. Sorry, did you want
So
to say?
there's a dynamic growth of cusps in galaxies. As they get smaller, the outer parts get stripped,
Sure.
and you end up with a cusp, a bare cusp.
Well, okay, good, right. So sort of along the same lines, in some sense, the difference here isn't that the ultrafaint dwarf has a higher density in the center. Again, I don't want to make that claim. We don't know that. It's just that you're able to observe smaller diameter, smaller radii because there's a lot fewer dynamics.
Yeah, I mean, somehow connected with that, it must be that, I mean, we could look at the cores of galaxies, which have very dense dark matter, but there we don't understand. There's so many stars and
Good.
crap going on.
No, exactly.
These things, there's somehow high density dark matter, but not a lot of stars.
Well,
right?
okay,
That's the
good.
claim,
So that's,
right?
that's
Is that right?
exactly the other thing.
Yeah.
Segue 1 has order, I think, 1,000 stars in it total.
Yeah.
Yes, it has very few stars, and there's very few self-interactions of those stars because of that. And so because of that, exactly, you can look at small radii. So at a fixed radius, it might still have a lower density than the Milky Way. We don't
But it's a
necessarily know.
fact anyway, I was just
Yeah,
curious.
yeah.
Okay.
Yep. Okay. You know what, let's not get into it. Yeah, there's complications from velocity, but yeah. As I said, density's high. Good. Let's keep moving. Okay, so as I said earlier, dynamical friction would in principle cause the stars in something like Segue 1 to slow down eventually, but the time scale for this is something like 10 to the 6 billion years or 10 to the 5 times the age of the universe. What am I plotting here? So on the x-axis is time in the past, right? So billions of years ago. On the y-axis is, let's say, a half-light radius of something like Segue 1. And so what's happening is that over time that half-light radius shrinks because the stars slow down and they fall in towards the center. And if we just take the current half-life radius and we propagate backwards, we'll find that that half-light radius would have been about equal to the scale radius of the thing. What is this? 1.5 million billion years ago, right? So 1.5 times 10 to the 15 years ago. That's nice, right? We know that it couldn't have formed more than that ago because stars don't form on the outside of halos. That's just not how galaxy formation works. But also, this is way more than the age of the universe. This isn't an informative, this isn't informative, right? The age of the universe is here. And so very little has happened in that time. But remember that dynamical friction goes as coupling squared, and so if we introduce some new force that's 100 to 1,000 times gravity, all of a sudden this happens a few billion years ago. And what this tells us is that if Segue 1 had formed more than a few billion years ago, which we know it did from metallicity, the stars would have had to start at some crazy radius in order to be where they are now, because otherwise they would have just deorbited into the center, right? Stars that formed inside the halo a billion years ago are now very far in the center. So this isn't consistent with what we observe, and so we can exclude a new force that's 1,000 times gravity on the basis of this not happening, right? On the basis of having finite half-life. On the basis of what the half-light radius is today. This would be great, and it would allow us to set wonderful constraints, but unfortunately it doesn't. And the reason it doesn't is that there's a minimum range for this effect to occur. What is that minimum range? It turns out to be about a milliparsec. Because within 1 milliparsec of a particular star in Segue 1, you can just look at this total mass of dark matter it's ever passed by in the 10 billion years it's been there, within a milliparsec of it. And at about a milliparsec, that total mass is about equal to the mass of the star. But the star can't change its velocity by more than order 1 if there's less than 1 solar mass of dark matter near it. Because in any interaction, it can only change the velocity of the dark matter by roughly its own velocity. So we can't possibly have this kind of effect, right, in spite of the generic dynamical friction result I just wrote down, once your force is too short range for this. There's just not enough dark matter for it to happen. And so the constraint I just claimed, right, that we can constrain new forces above 100 to 1,000 times the strength of gravity, is only going to hold for forces above about a milliparsec. This is a large part of why I didn't really focus on this, right, why I focused on the other part of my talk, that above a milliparsec, the resulting constraint is just not that strong. In particular, you'll notice, so on the right here is the sort of order 1 EP violating case. Here the colored lines under slightly different assumptions, you can ask me about them afterwards, are these dynamical friction constraints. And then the various black lines are constraints from, again, just combining dark matter only and standard model only things. And if you have order 1 EP violation, you'll notice that these constraints are just always subdominant, right? The dynamical friction just isn't quite strong enough to actually constrain forces the way we'd hope. If you have forces that are very EP conserving, right, if you have forces that really look a lot like gravity, you can start to exclude a little bit of new parameter space using dynamical friction, but it's pretty limited. Yeah. Good. All right, and so given that I'm already over time, maybe I'll go ahead and wrap up here, but there's other things I can say about this, ask me afterwards. What are the takeaways here? So dark matter can have long-range interactions, it can have long-range interactions with itself, it can have long-range interactions with the standard model. The self-interactions are constrained quite effectively by taking advantage of gradients in dark matter densities that change, for example, bullet cluster dynamics. But as you may have noted, right, so the bullet cluster dynamics and the ultrafaint dwarf result, they looked a lot like each other. All that mattered really is the scale of the system you're considering. We think that things like this extend to a variety of other things, in particular to various cosmological effects. And again, I'm happy to talk about these afterwards if you ask me. So we think probably you can set even better constraints using other systems. I've just shown a couple examples.
Sorry, wouldn't do better constraints, wouldn't you want to go to shorter ranges?
Yes, did I say longer?
Yeah.
Oh, sorry, I meant shorter.
You want to go to smaller systems,
No,
right?
I just
want to make sure I'm following.
Yep. Good. And then in the in the dark matter standard model interaction case, you could matter density and the universe not being quite old enough. If the universe was about 1 million times older, we'd be all set and we could constrain order 1 times gravity, but we're not that lucky. Okay. So that's the summary. I'm already over time. Thanks for bearing with me, and I'm happy to take questions. Yeah.
So, thanks for the talk, very nice. To state the obvious, you are comparing interactions with only one term in the Lagrangian. There are other terms. In particular, if the dark matter were a vector, you would have other couplings to electrical charge, for example. So you're focusing on a gravitational coupling to the standard model.
Okay, so I agree that generically you can have other kinds of potentials. Sure, yeah.
Yeah. And there are other terms in the standard model that it could couple to.
Sure, yeah.
This is very, very non-relativistic, right? So in the end, it's a potential, right?
Yeah.
And it's
The whole problem is non-relativistic.
yeah. I think the main thing is assuming that there's a coherent effect that the dark matter in some sense has to be charged, not under electromagnetism, but under something like the force is adding coherently, right? The force is proportional to the total amount of dark matter, right? That's a really big assumption. You could easily have.
Yeah, no, I agree, right? This applies only to some kinds of dark matter.
Yeah.
I like the U1B minus L example, right? This is a nice thing we can gauge, and it's not crazy to have dark matter that has baryon number, and then this will happen. But it's true that that's not true for all dark matter forces by any means, yeah.
you may have had it in one of your slides you skipped over, but there are upcoming observations which go to very small lambda, very small distances, mainly to look at the breaking up of stellar streams in our galaxy.
Yeah, so stellar streams are a fun thing, and that is one of the constraints that we want to look at in the future, that yes, there could be some fun effects on stellar streams here.
There are already observed gas.
Yeah, no, exactly.
Who
So
ordered that?
it's actually, I mean, okay, again, I don't like making strong claims, but in principle, some new force like this could help explain, from what I understand, or unexplained gaps in these kinds of stellar streams, yeah, where it seems like you have some very dense, strongly interacting objects that have to have passed through. That's right. Yeah. Yeah.
Could I ask about going to smaller scales? Because as I understood the bullet cluster constraint, a big point is that that the density of the dark matter is changing
Yep.
on the scale of the range,
Yep.
right? But
Well, sorry, it doesn't have to, well, I mean, okay,
That's
it's
my
changing
understanding.
continuously, I guess, right? The characteristic length scale over which the density changes can be much larger than the range.
yeah,
But there's still some change, yeah.
yeah, there's still some change,
Yeah.
but the effect goes like lambda over r star,
Yes.
as you emphasize, right?
Yeah, yeah.
So what I'm saying is that there aren't really small systems where, I mean, I'm asking, or I guess I'm asking. I mean, I can't. It seems to me that you know, a galaxy is sort of the smallest system that we could say that we're confident that the dark matter is changing significantly on that scale.
Yep.
And so how can you really find systems that are smaller where these effects are important? That's my question.
Good. So let me give two answers to that. One, so there is still quite a bit of space from cluster to galaxy, right? There's about a factor of,
These are
100.
clusters, okay, good,
Yeah.
yes.
Um,
Sorry.
But no, people have also tried to go within a galaxy, as you're sort of suggesting. This is one of the slides I skipped for time. They look at, for example, the Sagittarius dwarf spheroid, which is this dwarf that's fallen into the Milky Way and it's being turned into a stellar stream. And Mark Kamiankowski and company at some point showed that in the presence of a new force, even a tenth as strong as gravity, roughly, you would end up pulling the dark matter a little bit more towards the center of the Milky Way than the rest of the stream. And this would lead to an asymmetry between the forward and backward tails of this stream. And so they set constraints on new forces based on that. There's two difficulties with this, which is the reason I'm not emphasizing it, although it was on my plots, right, in the bottom right, it was this little band. Number one, there's some confusion about what actually happens as you ramp up the strength of this new force. In particular, there's a claim that if you actually get up to 1 times gravity, you pull the dark matter so far away that there's no longer a significant back reaction, it's too far away, and you no longer see an asymmetry. This is a weird claim. We sort of think that probably there'd be other systems that would be constrained in this case, but that's the claim as it stands right now. But the bigger issue with this and in general that comes up with galaxy constraints and with a lot of ways you might try to use this effect is that substructure really matters. Most of the dark matter within a short range of, for example, this dwarf, is going to be the dark matter of the dwarf, right? It's bound to it. And now you can no longer talk about the dwarf as moving in some background dark matter density that's not affected by it. Instead, there's a significant back reaction of the dwarf on the dark matter itself, on the dark matter of the Milky Way, you know, in general. In particular, let's see, I know for a fact this is true in the other example. It's probably true here too, although I'm a little bit less sure, but I think it's true here too. Actually, it almost certainly is, yes. That in the time that this dwarf is passing through a particular region of the Milky Way, the dark matter around it would actually fall into it and through it, completely rearranging the local dark matter density. And so this assumption I made previously that you have this dark matter density profile that's with larger densities at the center, larger densities at the center, smaller ones on the outside, that's what led to this new force. That completely breaks down because, again, in the time that the dwarf is in one area, it's rearranged the dark matter so that that's no longer true. And so you can't just naively extend what
So you're saying that if you had forces near this Kamiankowski bound or whatever, that it would screw up, I didn't understand the details, but somehow it seems like you're saying it would screw up dark matter so much that somehow their calculation doesn't apply, but isn't screwing up the dark matter a lot bad? I mean, isn't that itself some other constraint,
Okay.
probably?
Okay, good. So first of all, I want to make clear, I'm not by any means saying anything about the constraint they set, which was for infinite ranges. As far as I know, they did everything right for infinite ranges. We're concerned, right, with these finite ranges.
Okay, so you're saying.
And so you're screwing up a very small area of the dark matter density, right? You've locally messed up the dark matter profile, but we don't know that much about local dark matter profiles, right? There could be all sorts of substructure. The bullet cluster constraint is okay because as long as order 1 of your dark matter as a whole is in a smooth component, and that's what we get in simulations, granted, the simulations don't include new interactions, but nonetheless, as long as order 1 of your dark matter is smooth, everything holds up.
But doesn't that just mean that your range has to be larger than the size of one of these galaxies then? Or is it
Perfect.
stronger
Yes.
than that?
So once you are larger than about 10 kiloparsecs, I think their constraint holds up
Okay.
just fine.
Right, I see.
And that's
So
why,
I see, that's, so
Yeah.
you're just
So
saying
that's why
that's
I
the
put them off at
limit
10
of
kiloparsecs.
probably, that may be the limit of how far.
yeah, maybe you can do a little bit better, but below that, you start to really worry about back reaction effects.
Okay, thanks.
Again, I don't know exactly what other constraints you can set. The thing that we want to look at going forward, and that I think has a lot of promise to push to shorter ranges, is various cosmological effects, and in particular structure formation. We think that the impact of a new stronger than gravity force during structure formation should be larger and should be observable, and
Yeah.
so that's roughly
I
speaking
see,
the next thing we want to do. Based on very rough estimates, I think that can push down to order a few parsecs, maybe 100 parsecs. So we think you can probably extend this line down to here, and may probably have broadly the same behavior in shorter ranges, but again, this is speculative, we still need to do this.
Got it.
Other questions?
We don't actually know any limit on the clumping scale of dark matter. There's no limit. And so it could clump on really small scales.
Yeah.
As you say, and it could be small enough that these stellar streams, I mean, that's really small. If the gaps in the stellar streams as they currently, we don't have much data, but as they currently exist in the data, are due to dark matter, then they're clumping on these extremely small scales. And it could clump, it could be a power law, it could clump on even smaller scales, the size of this room, for example.
Right. I mean, the early universe, everything was smaller, right, and there's much more theoretical control. I mean, I think.
Right, so that's exactly why we
You
hope
can
that
just
we
put
can
these
push
forces
this down.
into your structure formation, and instead of falling in due to gravity, making overdense regions are going to be falling in with gravity plus this other weird force, and
Yeah, and so you modify,
luck
for
with
example,
that.
the gene scale in the early universe, and
Yeah.
we think that probably has observable effects
yeah,
on the CMB or on halo mass functions
Sure.
or similar.
yeah.
Any other questions? All right, well, thank you again.
Thank you. Very much.